look out into the void. We're living our entire lives on this tiny, fragile island of understanding, and it's surrounded by just a vast, uncharted ocean of the unknown. For literally thousands of years, humanity has been trying to chart this territory, right? We're building a map of human knowledge just to make sense of our reality. But the universe, it doesn't give up its secrets easily. No, it hides them in the microscopic, the macroscopic, and the profoundly complex.
And right now, at this exact moment, incredible things are happening entirely unseen. Just look at this number, 300 trillion. That is the exact number of neutrinos, these ghost particles born in the massive fusion furnaces of our sun that are passing through your body every single second. Every second. And you don't feel a thing, do you? Because to them, your body is essentially just empty space. But we know they're there, not through guesswork, but through the rigorous, verifiable integrity of modern science and these massive underground detectors. We literally map the unseen by trusting the data.
Okay, let's dive into this. Section 1, Mapping the Cosmos. Evidence in the dark.
So how exactly do we chart these extreme environments in space when we can't even see them with our own eyes? Well, we rely on hard observational evidence. Take the LIGO Observatory's detection of gravitational waves back in 2016. By measuring the minuscule, and I mean tiny, rippling of space-time itself, scientists got concrete, physical proof of black holes colliding millions of light years away. And the scale of the data we find is just staggering. Consider this contrast for a second. On one end, we've got Sagittarius A star, the supermassive black hole sitting right at the center of our very own galaxy, weighing in at an unfathomable 4.3 million solar masses. Massive, right? But on the other end, theoretical physics actually allows for micro black holes. A black hole with the mass of our moon would have an event horizon of just 0.1 millimeters. That's tiny! The laws of physics stretch across these unimaginable extremes, totally testing the very limits of our map.
But what exactly happens at that boundary? The event horizon is the absolute limit. It's the point of no return where the escape velocity actually exceeds the cosmic speed limit, which is the speed of light itself. Nothing can escape, absolutely nothing. But while the event horizon is a measurable boundary on our map, the singularity inside is where our map literally just ends. All that mass is squeezed into zero volume, and our mathematical models of general relativity, they completely break down. To understand what happens next, we desperately need an elusive unified theory of quantum gravity.
Moving right along to Section 2, the web of nature, decoding the biosphere.
Let's bring our focus back down to our home planet for a bit. As we zoom in on Earth, the way we map the biosphere requires that exact same rigorous dedication to verifiable data. The natural world is this dense web of incredible complexity, and decoding it means looking way past the surface to find the truth. For centuries, scientists basically map plant life based on what things looked like on the outside. Kind of makes sense, right? But the absolute integrity of modern data, specifically DNA classification, has completely overturned all that historical guesswork. True biological taxonomy actually proves that an oak tree is far more closely related to a pumpkin than it is to a pine tree. Wild, isn't it? When we follow the true genetic code instead of just our eyes, the map of life reveals these surprising hidden connections that totally redefine our understanding of nature.
And we can actually trace this genetic map back through a billion years of evolution. The scientific fossil record shows a super clear chronological progression. We start way back with the earliest green algae, which eventually evolved into simple non-vascular bryophytes like mosses. Then came the vascular plants, possessing the rigid internal structures they needed to actually grow tall. And finally, around 135 million years ago, the angiosperms arrived. These are the complex, flowering plants that basically dominate our world today. Step-by-step, hard, undeniable evidence builds the map of life.
But mapping our world also means confronting the data we'd sometimes rather not see. The integrity of information demands that we face reality head-on. Check out this incredibly stark visualization. Team Seas, which is an amazing fundraising project, set a highly publicized goal to clean up 30 million pounds of plastic waste from our oceans and rivers. It's a massive, truly commendable effort. But compare that against the staggering 60 million pounds of plastic waste humanity releases globally every single day. Good data shows us exactly what we're up against here, really highlighting the true scale of the challenges on our map.
Okay, Section 3, the human blueprint, constructing our reality.
So how do we take the raw materials of this planet and actually construct our modern reality? Well, engineering isn't just one isolated thing. It's this massive, deeply interconnected discipline. You've got civil engineering building our static infrastructure, chemical engineering is shuffling molecular bonds to process raw materials.
Mechanical engineering is out there converting energy into physical motion. Electrical engineering harnesses electromagnetism to power all our devices. And bioengineering merges biology directly with modern technology. Together, they form this continuous, highly optimized loop, converting raw energy and materials into the systems that literally keep modern civilization ticking.
And this brilliantly illustrates how engineering is constantly pushing into totally new frontiers. Take superconductivity, for example. When certain materials are cooled to extreme temperatures, they achieve zero electrical resistance and completely expel internal magnetic fields. This is a phenomenon known as the Meissner effect. And it's absolutely crucial because it bridges the macro world of heavy engineering right down to the micro world of quantum physics. This is what creates incredibly powerful technologies like the MRI machines that save lives every day, and it's paving the way for hyper-efficient electrical grids that will safely power your home in the future.
Which brings us to Section 4, the quantum frontier, harnessing the subatomic.
Let's shrink down even further and step into a place where classical rules just completely stop working. Now, what's really interesting here is the fundamental difference in how information is processed. Classical bits, the ones powering the exact screen you're looking at right now, are basically independent switches. They're either a 1 or a 0. Boom, simple. But quantum qubits, they exist in entangled superpositions, so they're essentially complex probability distributions existing in multiple states simultaneously. This allows a quantum computer's processing power to scale exponentially, potentially solving problems in minutes that would literally take a classical computer millions of years.
But listen, in a field moving this insanely fast, the integrity of information is absolutely paramount. We have to separate the hype from the verifiable performance. When you're benchmarking quantum hardware, raw physical qubit count just isn't the whole story. For instance, you might see a system with 127 physical qubits, but the true benchmark of power is actually something called quantum volume, which measures actual computational effectiveness and error rates. A system like Quantinuum's hit a quantum volume of 2048 with far fewer physical qubits simply because their noise and error rates were drastically lower. So in the quantum realm, quality matters just as much as quantity.
So where is this map actually taking us? Well, the industry roadmap between now and 2030 is heavily focused on reaching quantum utility. We're moving from the noisy machines of today, which boast maybe hundreds of physical qubits, toward fully error-corrected, fault-tolerant quantum computers. The ultimate goal here is scaling up to the estimated 1 million physical qubits needed to truly revolutionize fields like material science, cryptography, and chemical simulation by the end of this decade. I mean, this is going to completely transform the technology you use every single day.
And finally, Section 5, the edge of knowledge, uncharted territory.
We've mapped the biosphere, our incredible engineering feats, and even the subatomic world. But you know, the most exciting part of any map is always the edge. It's that uncharted territory where our current understanding fails and the true unknown really begins. As this quote perfectly captures, a theory of quantum gravity is the holy grail of theoretical physics. Right now, our map of the universe is essentially torn in two. We have general relativity to explain the massive scale of gravity and quantum mechanics to explain the tiny subatomic world. But at extreme scales, like right at the singularity inside a black hole, these two foundational models violently clash. They are completely, fundamentally incompatible.
And this creates some truly profound paradoxes that challenge absolutely everything we know. Consider the information paradox. If something falls past an event horizon, its unique quantum information seems to be completely erased from the universe, leaving behind only mass, charge, and spin. But a fundamental law of quantum mechanics called unitarity dictates that quantum information can never be destroyed. Never. This massive tension proves that our map of the universe is still fundamentally incomplete. We might eventually have to completely abandon one of our core laws of physics just to solve it.
Which leaves us standing on the very edge of the abyss. What happens to the map of human knowledge when the fundamental rules of physics must be rewritten? When the territory itself fundamentally changes, how will we redraw the lines? It's a stark and honestly thrilling reminder that no matter how much data we gather and no matter how detailed our models become, the absolute greatest discoveries are still out there, just waiting in the dark.